So today we continue on our journey into what happens when electromagnetic fields interact with matter. We started with the polarization field P, and we showed that that naturally comes into play when you just say that there is some kind of a dipole moment distribution that is distributed, might have a position dependence throughout some kind of a medium, and we're not really being very specific about how that responds, but we're just saying there is some kind of a dipole moment. And then if you integrate that over the volume, there's this trick that you can do, sort of a partial integration trick that allows you to then afterwards translate that into something that looks like a contribution due to surface charges and a contribution due to volumetrically polarization charges. Now, those surface charges and those polarization charges, they are not free to move. So that's why we usually use the subscript pol. And then we show that that the divergence of that polarization field must therefore look like that polarization charge, and there's pluses and minuses here somewhere. So it made a lot of sense to include that divergence in Maxwell's equations, and we ended up putting it in Maxwell 1, and we got an adjusted Maxwell equation 1 that just read that the divergence of that new field D, which is the contains both the original electric field and that polarizing field, and there's a 4 pi in there somewhere, now play the role of electric field, and then that would be equal to rho, but it's, or 4 pi rho, but it's not the rho that is the sum of the rho and the polarization rho. It's only the free charge. So that's a little tricky to think about. So I want to spend some time today on looking in particular what happens with an actual material. Let's make it explicit. Say what happens with P. What does the boundary condition look like? What does that sigma do? Where is it? What way does it point? And hopefully you'll have a better idea of what that D field is. I keep calling it the electric displacement field. I think the book calls it electric displacement. Once we've done that, hopefully you'll have a pretty good idea of how that D field is used, and then we can go on to doing the same thing, but now for magnetic fields. Now, magnetic fields are, well, again, they're cross products all over the place, but the starting point of talking about magnetic fields as they are interacting with materials, the starting points is very similar to how we started with our dielectric, with our electric field interaction with materials. So we'll start with some kind of a magnetic dipole moment that we can integrate over the volume to get some kind of a potential, and then of course that would be the vector potential, not the scalar potential. And we'll be able to do a similar thing, except of course because there's cross products, we have to do this little trick with the labeling the divergence with the field that it's operating on before we're allowed to do that, and then there's a minus that shows up. But the procedure in basic setup is very much the same, and you would not be surprised if you end up again with two terms. One term that has to do with how magnetic fields are interacting with the bulk of the material, so stuff that's inside, and then interacting with material that's on the top, or sorry, on the surface. And so we'll get two kind of contributions due to that. And then finally, we'll describe two materials that are very commonly used to describe materials, and then one is that basic dielectric, where that D field is just proportional to whatever the externally applied E field is. And then in magnetism, there's a similar thing that you can do. You can just say that there's going to be an adjustment made to the magnetic field that for certain materials we could just say is going to be proportional to whatever that externally applied magnetic field is. And then hopefully that'll bring us to the end of this chapter. Okay, so let's talk about the D field. Okay, so we had a oops. The D field and interaction of E with materials. All right. So just to remind you, we said that there is, let's say, some kind of a material, and there are dipoles everywhere. There are electric dipoles everywhere, and then we can describe that as a sum of two things. We have our rho that is induced, so that's the rho pole for polarization, and then there is an induced surface charge. So for instance, could sit here, right? So this, for instance, could look a little bit positive. This could look a little negative, and that would be the sigma pole, and they're related to that field P. So the P field, or the polarizing field, the P field, or yeah, I think you call it the polarization. And they're related to that sigma through that mathematical procedure I was telling you about earlier. So we have some sigma pole. Actually, let's color code that. Oops. Sigma pole, which is the dot product of that polarization with the normal. So at any point here, we can ascribe a normal to the surface, and then you take the dot product of P evaluated right at the edge of that boundary. So this is only valid at the surface. And then we have a rho pole that is equal to minus the divergence of that polarization field. And then taking those two things together, we can now have we can now use a modified Maxwell 1. So Maxwell 1, or Gauss's law, which now says that the divergence of that field D, which I shall describe in a little bit, 4 pi rho, and this is rho free, where that D field is the original E field plus 4 pi times that polarization field P. So that's how we modified Maxwell 1, but we didn't really say anything specific about how this field depends on the material. This is a very generic or general thing. But since we now have a modified Maxwell equation, so we have a modified Maxwell equation, we can use that modified Maxwell equation just like we were doing before. If we were doing a in integral form. So in integral form, this would be the integral of dA is 4 pi, and then that would be the volume integral of rho free, the volume, and this is the surface integral over the edge of that volume, and this is the volume integral. So we can do the same thing that we usually do when we have when we do electrostatics in vacuum. We can find the boundary conditions from this expression. So let's describe a boundary. So for instance, we have some kind of a boundary. Oops. Let's take this. Okay, so we have some kind of a boundary, and we have a medium number 1, and we have a medium number 2, and there's therefore a D field on here, and over here. And we can take a Gaussian surface and we can make this Gaussian surface, sit right here, such that it straddles the border between medium 1 and medium 2. And we can take this limit to 0. So we put these surfaces very, very close to the boundary. And then that means that we can calculate the flux, so the flux if you want, which would be the flux due to that field d integrated over the surface area. And then if we take the limit that surface area is small enough such that we can assume it is uniform, usually what you will get is you just get a d times a. Let's call this thing a. All right, so we get a d2 times a minus d1 times a is the charge. Now, this enclosed charge would be the charge that sits here right at that surface, and that will be 4 pi times q, and that will be q free. We can divide out d2 minus d1, and we get 4 pi sigma free. Okay, so that's our boundary condition. So if we have any kind of transition from a material 1 to a material 2, now unless that there is some sigma free involved, or a medium with a polarization that is not 0, we have to start paying attention to the D fields rather than the E fields. Okay, so let's see this thing in action. All right, so let's say a capacitor. Example, a capacitor. Now we're gonna do what we usually do. We'll say, well, let's call this thing, actually, let's call this thing negatively charged, call this thing positively charged. Of course, they are actually sitting on the inside. I'm being a little sloppy. Okay, so we'll do that here. Okay, and that's because we have placed some potential here. So there's a potential here, some delta V, and as a result, we'll get an electric field, and the electric field would look like this, And we're assuming again parallel plate configuration, so no edge effects. If you really want to, there should be E fields that are doing this, but let's only worry about the inside. Okay, so now your mission is the following. So we're going to modify this, and we're going to put a material inside. So we'll now place a material inside the capacitor. All right, so we'll have a we'll have the same plates, and the material we're going to put is going to be in here, and we're not filling the entire region, meaning we're not going to go all the way up to the plates, but that is just to make our discussion a little easier. And this one is still positively charged, sorry, negatively charged. And this one is positively charged. I believe that's how I had it set up. Yes. Okay. And now draw E in the region where we have vacuum. So let's call that, we have the original E. Sorry, I had it in blue. Where's my eraser? So draw E, and then also draw the field E in that region where that material is placed, the green material, and then also draw P and draw sigma polarization in this setup. Okay, so this is I find surprisingly tricky. So let's go over this step by step. First, we need the boundary condition. So the boundary condition. So if we take a Gaussian, if we take a Gaussian surface, where we are. So we do the Gaussian surface here, and we have an electric field originally. That's the field. That's the blue field. That is like this. All right. Then if the region between the green material and that top plate is vacuum, then there it means that D is equal to E. So let's call the blue field, let's call it field 1, for instance. So we'll call we'll say basically D1 is E1, and that's the blue field. And then we know from the boundary condition that the boundary condition says that D1 minus D2 is equal to 4 pi sigma free. Now, I don't think I was really explicit about what kind of material I was talking about, but let's assume that this is an insulator. Oops. Let's assume that this is an insulator, because things become different when there is a when there are free moving charges, right? So if it's an insulator and this thing is 0, so therefore the electric displacement field in the green material is equal to the electric field, the displacement field in the blue material. So our D1 is equal to D2. Now D2, by definition, is equal to E in the field number 2, in region number 2, plus 4 pi times that P field in the region number 2. And since D2 is equal to D1 is equal to E1, finally our E2 is going to be E1 minus 4 pi P2. Okay. All right. So what does that mean? Well, if P2 is a field that's pointing in the same direction as E2, then that means that E2 is smaller than E1. Okay, so let me say if P2 is pointing in the same direction as, in same direction as E2, then actually E2 is going to be smaller than E1. All right. Well, what does that mean? Well, that means that the field lines will be spaced further apart. So 1, 2, 3. So that's the field in region number 2. Now, the signs here get really tricky, right? So what does that mean for the polarizing field? Well, if E2 is smaller than E1, then that means that P2 is pointing in the same direction as that field, and that's why the polarizing field is weird, right? So P2 is actually also in this direction, P. That's the P field. And now finally, we need to say something about the, where's my expression? Here we go. Sigma polarization. Okay, so sigma polarization is the normal dotted with the polarizing field. Okay, so that means that sigma polarization is positive here, and it's negative here, right? Because the normal points in this direction. Okay, so this is sigma pol. The signs here might be surprising to you, the fact that the P and the E field are pointing in the same direction, but that's just the way it is. And it's because it's not a regular electric field, it's the polarizing field and it's the displacement field. Now, the fact that this thing starts to become positively charged makes a lot of sense if you think about this thing starts being positively charged, makes a lot of sense because actually all the material in here, right, has free charge carriers, that is to say, charge carriers that are free to move around atoms, and they themselves will be experiencing the electric field that's being applied externally. So therefore, opposites attract. You'll get more pluses on this side and more minuses on that side. So that's how those fields work. So what does that mean for the potential? Well, this is kind of interesting. So remember that the potential is minus the line integral of EDL. So that's delta V. So the electric field is smaller in the green region. So that means that the capacitance, which would be Q over V, if the voltage between the two plates therefore is smaller for the same charge stored, then it means that the capacitance actually goes up. All right, so so delta V becomes smaller due to the material, and therefore C becomes larger. And this is why when people make proper capacitors, they'll actually make these capacitors not with vacuum in between, but they'll put material in between. And now we should talk a little bit about materials, but not too much. So the most basic dielectric material is where for an isotropic dielectric, that D field is epsilon times the E field, and now that E field is the internal E field, right? So if you want, you can basically therefore find P in terms of this epsilon. It's just a different way of formulating the way that materials respond. And that epsilon now is your relative dielectric constant. And your capacitance is going to be proportional to that epsilon. Okay, so that's for dielectric. Now, let's see, that's probably enough for one page. Okay, so let's do, how about metal? Oops. So we do the same thing. We have our capacitor plates, and now our green material is a metal. We know that E is 0 there. Okay, so the boundary condition is again that your D field has to be, oops, sorry, D2 minus D1 is 4 pi sigma free. Okay, so now we have actually induced charges that are free here. And then, so this was originally positive, this negative. So now we get free charges here, and they're free to move. And there's no field inside, so it's different. So finally, we do have for dielectric materials, we also have another quantity, and that's the psi E, which is the electric susceptibility. Electric susceptibility. And that is the proportionality between the polarizing field and the E field. So that's just another way of writing it. And in that case, you can solve using our displacement field and our other definition for a way to quantify materials, and you'll find that the relation is that it's that epsilon minus 1 over 4 pi, and that's the previous dielectric constant we encountered before. Let's talk about magnetism. And materials. So there's this current density in general that you could describe as a sum of the original current density that we always talked about. That's what we now call J free, and J free is the is that part that is involved with the flow of free charges, right? So for that, there's a continuity equation. So continuity equation. That that says that the divergence of J free is actually people like writing this plus rho free is equal to 0. So that's that free. Now there are other contributions as well. For instance, there's a convection, which we usually throw out. The book describes does not really do anything with it. I think that's a reasonable thing to do, because convection is really it's the physical movement, right? It's physical movement of a medium, with charges embedded in it. I think it's perfectly reasonable to just kind of incorporate that in J-free, right? Because whether the charges are bound to the medium or whether they're not bound to the medium, if they're moving with it, you could still describe that as charges that are actually moving. They might actually be bound to the medium, so they might themselves not be free to move, but there are probably ways to account for that. So so we're going to ignore that part. But we should talk about something else. So for instance, we're going to go back to our capacitor, and we've got our medium here. And now if we turn on the power supply, there will be a buildup of rho and sigma polarization and P field. So let's look at what that would look like. So we know that ddt of we know that rho polarization is minus the divergence of that polarization field. So if we take the derivative here, ddt, and we can also take ddt here, and then we can bring the ddt in. Now we have minus the divergence of the ddt of p. And now we can bring this over to the other side, and we can say ddt of the rho polarization plus the divergence of dp dt is equal to 0. Okay, that looks very similar to our continuity equation, right? You see that continuity equation is here. And now we have a similar equation here for the polarization charge, so not free charge. So that means that we can call this thing the polarization current, so J polarization, such that there is a continuity equation that looks just like before. So ddt rho polarization plus the divergence of J polarization is equal to 0. So that's the continuity equation for polarization. Okay, So we can add that to our sources of current, right? So we have now that's our third source of a current. We have numbers 1 and numbers 2 here, but we're throwing away the convection. Okay, now comes the really tricky one. So magnetization. So in order to walk you through what that looks like, I want to invoke the argument that we were using before for polarization. Oops. So when we were doing polarization, we said, well, there is some kind of a dipole moment distribution that, when integrated, gives you the total potential. So that gave us a phi, which was the integral of that polarization, which was P, and then dotted with the R minus R over, oops, sorry, that's not true. That's the wrong erasure. R minus R prime cubed, and then integrated over volume. And then we rewrote that as our polarization dotted with the gradient of 1 over R minus R prime d3x. And then there was this, really funny integration by parts that you could do, where you could basically pull the nabla out and then rewrite the first one into a surface integral and the second one into a volume integral. And we got these two terms. We got a P dotted with a normal integrated over the surface over R minus R prime. And this was integrated over the surface. So that's the edge of some volume minus, and then, oops, minus the, only one minus, the volume integral of the divergence of P. I might be missing primes here, but if you want, you can revisit that from the previous lecture or the notes. But the point is that that's how we went, and then we said, okay, this looks like sigma polarization, and this looks like, together with the minus, rho polarization. So now for magnetism, we're going to do something similar. So the starting point here was the potential of a dipole, which was phi was d dotted with r vector over r cubed. And now we're going to do the same thing for magnetism, but now we're actually using the vector potential. And that's the vector potential due to, actually, let me use m r cubed. So it has the same basic setup, except now there's a cross product instead of a dot product. But we're going to do the exact same thing. We're saying, okay, we'll have a magnetic dipole moment distribution and then that means that we need to write our vector potential as the integral of that magnetic dipole moment density, okay, which we're going to call M. So that's our M field, and then we need to cross that with R, R prime over R cubed. And now we're going to do the same thing. We're going to call that, oops, there's an integral here, dx prime. And let's actually write that out correctly. So that's r vector minus r prime. And now we're doing the same thing. We are again saying, okay, this is m crossed with the divergence of 1 over r minus r prime integrated over the volume. And now, of course, because they're cross products, oops, they're cross products here. When we do that integration by part, we need to actually reverse the role of reverse the order of the cross product in the curl. So remember, oops, let me do that in a different color. The trick with subscripting E and B, and then manipulating those across your cross products to using the regular cross product rule. At some point, you need to invert. You have the cross product on with the nabla operator on the right of the thing that it's trying to act on the left. So at that point, you reverse the order and you pick up a minus sign. So then what you get here, it follows the exact same recipe, except now we'll get a sign difference. So we'll have m with ds over r minus r prime, okay? And that is integrated over the edge of that volume, plus the volume integral of the curl of m over r minus r prime d3x prime, and there's probably an s prime here as well. Okay, so this if you remember how to calculate vector potentials from current distributions and from magnetic moments, you'll see that this is basically current, but it's now the magnetization current. And this is the surface magnetization current. Surface magnetization current. Okay, so that's the way that we can quantify them, and then the surface magnetization current we call K, and that is, in this case, is evaluated at the surface, and this one is for the bulk, and that's J. It's C in the curl of M. Now this is J mag, oops, J mag, and this is K mag. Okay, so the procedure is very much the same, but because there are cross products all over the place, it becomes a little bit more messy. All right. So then what do we get? Well, we have now this is our number 4. So inside the material, we have, so we're going to change ampere Maxwell. Changing ampere Maxwell. So we had a already a curl of B minus 1 over C dt. Okay, it's 4 pi over C. All right, now we will have our J free, that's our original freely moving current density. That's the one we have from magnetostatics and stuff in vacuum. And now we also have our dp dt, which is our polarization current. And we also have our magnetization current. So that's our curl of M. Okay, that's the J magnetization. And again, we're forgetting about the convection term. All right, so now you should be able to see that we can move into the curl here. We can bring the, let me underline this, we can take this term together with the 4 pi over C, and you see that the C and the C cancel, and I can bring it over to the other side, and now I would get minus 4 pi M. Okay, so that's how we put this term on the left. Now we also have a minus 1 over C dE dt. Now the dE dt we can modify with the dP dt again as per usual, because we know that E plus 4 pi, oops, sorry. That's the polarization field. I believe my signs are correct. I just miss a derivative. Put that in there. ddt. Okay, so let me see. Got the ddt, got a 4 pi, got a C. Yes. All right. So that's the left-hand side. And now we are left here with 4 pi over C. J free. So J free is still the original J free that we had, but now we should recognize that this here, this term in green, is the D field. So that's our original D field. So the electric displacement field, and this we can call something different. So let's call this the H field. I think they call it magnetizing field, or I think terminology becomes a little hazy at some point. But now we have a modified ampere Maxwell. That says that the curl of that new field H minus 1 over C ddt of that field D is equal to our original 4 pi over C J, but now we should specify that this is J free. It's the original J that we had, but now it's included there. So that's pretty cool. Let me write that down. So that's pretty cool. Okay, we can now also, because this is in the original form of Ampere-Maxwell's law, we can again do things with boundary conditions, and usually we'll have a material number 1 here and a material number 2 here. And now, of course, we can't do anything with Gauss's law, but we could do something with our an Amperian loop. So, for instance, we could put a little Amperian loop here, and take appropriate limits such that we take this thing down to here. Then we get one boundary condition that says that the tangential field is continuous. So B1 tangential is B2 tangential, and yeah, and the appropriate boundary condition for the H field is, and that one comes from Gaussian type formulation. No, it's cross, sorry. Cross with N is 4 pi over C, and this is where our K shows up. So that's K magnetization. This becomes, sorry, K free. Ooh. That's surface current density, sorry. K free. Okay, so it's a similar similar situation. So we have a boundary condition that will tell you how the H fields are related. And for instance, if one of them is in vacuum and the other is in a material that has magnetic properties, then we can use this to figure out what's going on. Now, K free, that's surface current density. Okay, so integrated over surface will give you the total current density. Okay, so then the most simple magnetic material is so compare is where M is equal to where's my prefactor? Oh, sorry, not M. That's why I couldn't find it. That B is mu times H, where mu is the magnetic relative magnetic permeability, I believe, permeability. I can never remember which one is permeability and other is permittivity. One is for magnetism, the other is for electricity. Okay. Well, so that brings us to the end of this chapter. So we've generalized. Maxwell's equations to include a realistic and quite general description of magnetic and electrically more interesting materials, and you should be able to do most problems with this. Now, word of caution, there is, so actually let me pause my share. Okay, so word of caution, there is in the book, there's an entire chapter, as I was saying before, devoted to solving all of these kind of boundary value problems. I think at some point it becomes diminishing returns. I think once you've done it once, I don't really see the point of doing it for more interesting geometries, other than, you know, it's good practice. But I don't want to necessarily weigh you down. So if you want to, you can read those chapters on your own. But rest assured that it's just solving Maxwell's equations, these modified Maxwell's equations with these modified boundary value problems. And you see, even for the parallel plate capacitor, it becomes quite hard to visualize what exactly is going on. But now at least you have the basic ingredients to do that. So that brings me to the end of this lecture, unless there are more questions. All right, so then have a good evening if you have to leave. Otherwise, I'll see you on Wednesday or in office hours. Bye.